In the previous video, we introduced parametric curves and we discussed already how to sketch such curves. However, to get a better kind of sketch, we will need tangent lines, and in this video we're going to discuss how to find them. So let's say to start with that we have a certain parametric curve that turns out to be the graph of a function. In other words, it passes the vertical line test. Each vertical line intersects a graph in at most one point. Then that means that we could eliminate the parameter t and rewrite the curve with an equation of the form y equal f of x. In other words, the curve is a graph of the function capital F. But y is g of t and x is f of t, and so I can differentiate this equality with respect to t, and I get g prime of t on the left hand side, and on the right hand side I have to use the chain rule, and therefore I get the derivative of the function capital F evaluated at little f of t multiplied by the derivative of little f. And if f prime is non-zero, I can divide both sides by this quantity, and I get capital F prime at x, because f of t is x. This is g prime of t over f prime of t. But capital F prime of x is really the slope of the tangent line to the graph, and therefore the slope of the tangent line at that particular point, x f of x, in other words at the point xy, is, well, the rate of change of y with respect to x, dy over dx, but that can be expressed as the derivative of y with respect to t divided by the derivative of x with respect to t. So in other words, we wouldn't really need to eliminate the parameter t to calculate that. If x and y were given to us as functions of t, we can just take the derivative of y as a function of t divided by the derivative of x as a function of t, and that gives us the slope of the tangent line at the point of parameter t. And so more generally, if we have a parametric curve that now we no longer assume to be the graph of a function, the slope of the tangent line at a point of parameter t is simply y prime of t divided by x prime of t, evaluated at the particular value of the parameter, assuming of course that this formula makes sense, that is, assuming that the derivative of x with respect to t is non-zero. So this is how we're going to get the slope of the tangent line at a particular point of a parametric curve. Now note that in particular, when the derivative of y with respect to t is 0 and the derivative of x is not, then we get the slope of the tangent line is 0. In other words, we get an horizontal tangent. And similarly, if the derivative of x with respect to t is 0 and the derivative of y is not, then we get something non-zero divided by something going to 0, and therefore we get something that goes to infinity. And that means that if the slope goes to infinity, that means we have a vertical tangent. So in this type of situations, we'll get a vertical tangent to the parametric curve. Now let's look at some example where we're looking for an equation of the tangent line to a parametric curve, starting with a case where the parametric curve is given by x is t squared plus t, y is t squared minus t, and we're looking for the tangent line at the point of parameter t equals 0. Well, you see that if t is 0 and we plug that in x and y, we get 0 for x and 0 for y, so we are looking for the tangent line at the point 0, 0, which belongs to the curve. To find the slope of the tangent line, we need to calculate dy over dx when t is 0, and this is obtained by calculating y prime of t and x prime of t, and dividing y prime by x prime, and then plugging t equals 0 in this. Y prime here is 2t minus 1, x prime is 2t plus 1, and when we plug t equals 0, we get negative 1 over 1, therefore negative 1. Therefore, the tangent line we are looking for is the line through the point of coordinates 0, 0, and of slope negative 1, in other words, the line y equal negative x. So this is the graph of the parametric curve. We're not going to discuss how to obtain that in this case, and this is the line y equal negative x, in other words, a tangent at that particular point 0, 0. Let's look at another example where x is e to the square root of t and y is equal to t minus natural log of t squared. And we're looking for an equation of the tangent line at the point of parameter t equal 1. So if I plug t equal 1 in x and in y, I get e to the 1, so just e for x, and for y I get 1 minus log of 1, and log of 1 is 0, so I get just 1. So the tangent line is going to be a line through the point of coordinate e1, and now we need the slope of that line, which is dy over dx when t is 1, and that we can obtain by dividing y prime by x prime when we differentiate with respect to t, and then plug t equal 1. So y prime in this case, derivative of t is 1, derivative of ln of t squared, we can write that 2 ln of t, and therefore we get 2 over t for the derivative of ln of t squared. And the derivative of x is a composite. We have the square root of t plugged inside the exponential function. So we use the chain rule, we get e to the square root of t multiplied by the derivative of square root of t, which is 1 over 2 root t. And then we need to plug t equal 1 in this. So if we do that, we get negative 1 at the top and e over 2 at the bottom. And therefore we get, for the slope of our tangent line, negative 2 over e. So now the tangent line is the line through the point of coordinates e1 and of slope negative 2 over e. Therefore its equation is y minus 1 equal negative 2 over e multiplied by x minus e.